When astronomers first detected a mysterious object speeding through our solar system in 2017, they were stunned. It wasn't orbiting the sun like anything we'd seen before. Instead, it was moving too fast on a path that came from beyond our solar system. They named it Oumuamua, Hawaiian for a messenger from afar. But that messenger carried more questions than answers. It was oddly shaped, completely silent, and showed no visible tail or gas. Yet it moved as if something was gently pushing it forward. Some scientists proposed exotic explanations. Maybe it was made of rare ices, or perhaps sunlight itself was nudging it like a sail. But others asked a far bolder question: what if Oumuamua wasn't a rock at all? Could it have been an artificial probe sent intentionally, or accidentally, by another civilization? Since then, 2 more interstellar visitors have entered our solar system: Comet Borisov in 2019 and Comet 3 I-Atlas in 2025. Each one arrived with its own mysteries, and together they've changed how we see our place in the galaxy. So, what are these visitors really? Alien messengers, or just wandering debris from distant stars? Let's uncover the truth. For billions of years, our solar system has quietly orbited the Milky Way, a tiny oasis surrounded by uncountable stars. But sometimes, something drifts in from the darkness beyond, an object on a strange path, moving too fast to have ever called our sun home. These are what astronomers call interstellar visitors, travelers born around other stars, wandering through the galaxy until chance brings them here. They are relics from distant solar systems, fragments of planets and comets that were flung out by gravity long ago, now crossing our skies for only a brief moment before disappearing forever. So how do we know an object comes from another star? The key lies in its trajectory. Every asteroid or comet bound to the sun follows a closed elliptical orbit, but an interstellar object moves on a hyperbolic path, open-ended, meaning it entered our system once and will never return. When scientists first tracked Oumuamua's motion, they noticed its excess velocity, about 26 kilometers per second, faster than the escape speed of the sun. That single detail proved it was not gravitationally bound, a traveller from the vast interstellar sea. Confirming that status takes precision, dozens of telescopes across Earth measure its motion night after night, refining the orbit until no doubt remains. If the eccentricity, the stretch of its orbit, is greater than 1, it's officially interstellar. Oumuamua had 1.2, Borisov's was 3.4, and the latest arrival, 3 I-Atlas, an astonishing 11.4, speeding through at over 100,000 kilometers per hour. Among all the interstellar wanderers we've identified, one arrival changed everything, the first ever seen and still the most mysterious of them all, Oumuamua. When the Pan-STARRS survey telescope in Hawaii spotted a tiny point of light speeding across the sky on October 19, 2017, astronomers knew they had stumbled on something extraordinary. That object would later be named Oumuamua, the first confirmed interstellar visitor ever detected. From that moment on, it challenged everything we thought we knew about cosmic wanderers. Oumuamua was first catalogued under the provisional designation 2017 U1. By analysing its motion over subsequent nights, astronomers rapidly realised it was not bound to the sun. Instead, it was on a hyperbolic trajectory, a one-time pass through the inner solar system. Pan-STARRS initially noted it as an asteroid, but the unusual speed and path triggered further scrutiny. NASA later referred to the detection as history-making, the first concrete proof that objects from interstellar space could visit our neighbourhood. At discovery, Oumuamua appeared faint. No obvious signs of gas or dust, no tail, nothing like a typical comet. Its reddish hue, derived from spectral measurements, suggested a dark, organic-rich surface, perhaps weathered by cosmic rays over eons. This faint dot was moving at tens of kilometers per second, crossing our skies faster than we could fully catch it. Astronomers scrambled to observe it using large telescopes around the world, from the Very Large Telescope VLT in Chile to the Keck Observatory in Hawaii, trying to squeeze every photon out of the fleeting visitor. In those early observations, one of the first oddities became clear. As Oumuamua rotated, its brightness varied dramatically. It was not a constant flicker, the intensity would swing by a factor of 10, a tenfold difference between brightest and dimmest. Such a variation implied a highly elongated shape. To understand that, picture turning a long rod end over end. Sometimes you see the thick side, sometimes the thin edge. That's what the brightness swings suggested. Oumuamua might be cigar-shaped, or perhaps something flattened or even pancake-like. Early shape estimates placed its aspect ratio at somewhere between 6 to 1 to 10 to 1. Far more elongated than any known comet or asteroid in our solar system. Because its rotational period was irregular, it appeared to be in a chaotic tumbling state. Modelling the shape became complicated. But even with those complications, the data were consistent with an extreme elongation or flattened geometry. Unlike anything familiar, the light curve anomalies were so pronounced that some skeptics suggested the object might not even be a solid rock, perhaps a thin structure like a sheet. Yet all models had to respect one fact: the light curve fluctuations matched expectations of a rotating, tumbling object, not something artificially pulsed or modulated. So far, so mysterious, but the mystery deepens when we move to its motion beyond what gravity would predict. Once Oumuamua passed perihelion and began heading outwards from the Sun, astronomers expected it to slow under solar gravity. Instead, they measured a tiny but consistent extra push, a non-gravitational acceleration component. This effect was small, but statistically significant. In the 2018 paper by Marco Micheli et al., the data indicated that Oumuamua's velocity was increasing by just enough beyond gravity to demand explanation. Strikingly, however, no cometary coma or tail, no sign of gas and dust being expelled, was ever seen, not even faintly. In conventional comets, sublimation of water or CO and CO2 ices provides thrust. Here, no such outgassing was observed even under deep scrutiny from large telescopes and sensitive instruments. That absence sparked heated debate across the astrophysics community. Some skeptics argue the acceleration detection might be a measurement artifact, but the consensus is that the effect is real within observational error margins. The question became, what's pushing it? Leading natural explanations were proposed, none simple, all speculative, and some even more exotic ideas. One of the boldest suggestions came from Harvard astrophysicist Avi Loeb, who proposed that maybe Oumuamua was a light sail, a piece of technology pushed by solar radiation pressure. This idea captured the public's imagination, but it faces steep observational challenges. To act as a sail, it would have to be extremely thin, large, and show signs of structure or orientation control, none of which were seen in any data. Yet, over the years, scientists have pursued more grounded hypotheses to explain the acceleration without invoking aliens. One of the most promising is the radiolytic hydrogen H2 outgassing model. Here's how it works. Over millions or billions of years, cosmic rays can penetrate the object's surface layers, splitting molecular ices like water or organics and producing molecular hydrogen. This trapped hydrogen accumulates until internal pressure forces it to escape, creating a gentle thrust. Because hydrogen is a light gas, even small leaks might produce measurable acceleration, and because it is colorless and transparent, the resulting outgassing could be virtually invisible to telescopes, producing almost no detectable coma or dust. Recent works like Bergner et al. Have refined this model, showing that under certain conditions and porosities, the amount of H2 required to match the observed acceleration is plausible. They showed that the rate of release might be small but cumulative over distance, and the gas escape could be so diffuse that conventional instruments might not detect it. This scenario aligns with the absence of a visible tail and with the magnitude of the non-gravitational effect. Other ideas include sublimation of more volatile ices like CO or N2 hidden deep within, or a phase change in exotic ices such as amorphous to crystalline that releases gas. Some have speculated about disintegration of small bits, microjets of dust or gas too faint to detect. But these models must navigate tight constraints. They must explain the acceleration, avoid contradicting the lack of detected outgassing, and be consistent with the observed brightness and spectral behavior. Thus far, the radiolytic H2 hypothesis stands as one of the more compelling, physically grounded proposals that doesn't rely on engineered structures. With all this strangeness, weird shape, acceleration without visible outgassing, it's no wonder speculation arose. Could Oumuamua be a probe, a piece of alien technology drifting through space? Proponents of this idea suggest that perhaps it is a light sail, or some probe with internal propulsion, or even a partially operational artifact. But scientific scrutiny demands that we see evidence, not just anomalies. Here's where observations argue strongly against the artificial hypothesis. First, no radio signals or beacon transmissions. Breakthrough. Listen used the Green Bank telescope to scan Oumuamua for radio transmissions. Nothing was found. No repeating signals, no bursts, no signs of technology. If it were an operative probe, many expected at least some form of emissions or telemetry. Second, no visible engineering signatures or modulated light patterns. If it were a structured object, we might expect specular reflections, regular rotation signals, or anomalies in its light curve that signal artificial design. Instead, its light curve is consistent with natural tumbling and random brightness swings. Third, extreme thinness and durability issues. For a passive light sail to achieve the observed thrust, it would have to be extraordinarily thin and wide. But such a structure would be vulnerable to collisions with dust, radiation damage, micrometeoroids. Over the interstellar journey, durability would be a huge problem. Also, a sail often implies orientation control or stabilization, but no signs of attitude adjustment or directed thrust were detected. Fourth, while the anomalies are intriguing, researchers generally prefer explanations that invoke fewer unknowns. Radiolytic outgassing, volatile release, or sublimation variants remain plausible. Until we find positive evidence of technology, and not merely anomalies, the scientific default remains. Oumuamua is natural. Over time, as new data and models emerge, the balance of probability has shifted further toward natural hypotheses. Yet, Oumuamua remains a fascinating, enigmatic object, the first emissary from beyond our sun, challenging our models and inspiring curiosity. In August 2019, a quiet observer at an amateur observatory in Crimea pointed his custom-built telescope toward the dawn sky. His name was Gennady Borisov, and what he saw would make astronomical history. A faint, moving blur. Just another potential comet, he thought, but as astronomers checked its orbit, they realized it was traveling far too fast to belong to the sun. This was not a local wanderer, it was 2I Borisov, the second confirmed interstellar visitor, and the first ever seen behaving like a comet. Unlike the mysterious Oumuamua 2 years earlier, Borisov made its identity clear almost immediately. Through small telescopes, it already showed a fuzzy envelope, a coma, and a thin tail of dust streaming behind it. It looked for all the world like any ordinary comet, except for one crucial fact. Its orbit was open, hyperbolic, and inbound from beyond the solar frontier. Borisov had likely spent millions of years drifting through interstellar space before a lucky gravitational nudge brought it near our sun. Professional observatories quickly turned toward it. The Hubble Space Telescope, the Keck Observatory, and the Very Large Telescope all captured it in remarkable detail. For the first time, humanity could study, directly, the nucleus and gases of a comet from another star system. It was, in a sense, the closest look we've ever had at the raw ingredients of an alien solar system. At first glance, Borisov appeared unremarkable, a small icy nucleus, maybe a kilometer wide, wrapped in a pale blue haze of gas and dust. But that ordinariness was precisely what made it extraordinary. Unlike Oumuamua's dry, rocky mystery, Borisov was alive with activity. It released water vapor, carbon monoxide, and dust grains, forming a glowing coma and a tail that stretched hundreds of thousands of kilometers long. Its behavior was textbook cometary physics. Even its brightness variations followed expectations for a venting, spinning comet nucleus. The Hubble Space Telescope captured stunning images, a tiny white dot of a nucleus enveloped in a perfectly symmetrical coma. Later images taken after perihelion showed the comet slowly fading and fragmenting, leaving behind a trail of dust still visible months later. For many scientists, Borisov was the control sample we needed, proof that interstellar objects could look and act exactly like our own comets. But the real intrigue came when observatories began dissecting Borisov's light. Spectroscopic studies from ALMA, the Atacama Large Millimeter/Submillimeter Array, revealed a startling result. Borisov was releasing carbon monoxide, CO, at levels several times higher than any typical solar system comet of similar size. In fact, its CO to water ratio was among the highest ever recorded. That chemistry told a deeper story. Carbon monoxide freezes only in extremely cold environments, below -250 degrees Celsius, far colder than the region where most comets in our solar system formed. So Borisov likely originated in the outermost reaches of its native star system, perhaps beyond the equivalent of our Kuiper belt, where the young star's light was weak and ices could condense without evaporating. In other words, Borisov preserved the chemistry of a world even frostier than our own cosmic outskirts. It carried within its frozen body the signature of a star born under different conditions, maybe a smaller, cooler red dwarf, or perhaps a more distant part of a sun-like system. ALMA also detected the gas HCN, hydrogen cyanide, and hints of formaldehyde, common in solar system comets but appearing here in unusual ratios. Together, these patterns confirmed that while the same broad chemistry existed beyond our sun, the relative mix could differ, each planetary nursery writing its own chemical recipe. In short, 2I Borisov is entirely natural, a pristine fragment of another planetary system wandering freely through the galaxy. Borisov's visit ended quietly. By early 2020, it had faded beyond detection, leaving behind a faint dust trail and invaluable data. But its legacy endures, the first confirmed comet from another star, a natural messenger of cosmic commonality. In July 2025, sky surveys detected a new interstellar visitor. Unlike the silent wanderer Oumuamua or the CO-rich comet Borisov, this one was unusually active from the start. It was designated 3I/Atlas, the third known interstellar object ever to enter our solar system. On 1st July, the Atlas Asteroid Terrestrial Impact Last Alert System survey telescope in Chile flagged a faint diffuse object in the night sky. Catalogued as C/2025N1 Atlas, it was soon recognized not as a typical comet, but as a hyperbolic visitor from the stars. Precovery images later showed that it had been visible as far back as May 7th, 2025, when it was around 6.4 astronomical units from the Sun, already active then, hinting at volatile-driven activity deep in the cold. Because Atlas was active so far out, scientists suspected it might contain volatiles more exotic than water, perhaps CO, CO2, or other ices that sublimate at much lower temperatures than water. As observations mounted, the picture grew richer. On July 21st, 2025, the Hubble Space Telescope captured one of the clearest images of 3I Atlas to date. The image showed a teardrop-shaped cocoon of dust streaming from what is believed to be its underlying solid, icy nucleus. This cocoon wasn't a classic symmetric coma. The dust was biased in the sunward direction, indicating strong outgassing toward the sun, pushing material outward. Thanks to Hubble's sharp resolution, astronomers bounded the diameter of the nucleus to an upper limit of about 3.5 miles or 5.6 kilometers, though it may be considerably smaller. Even more, the motion of Atlas, traveling at about 130,000 miles per hour, is one of the highest velocities ever recorded for a solar system visitor, underscoring its deep interstellar origin. Here's where Atlas truly surprises us. Using the Neil Gehrels Swift Observatory, astronomers detected ultraviolet UV emissions consistent with hydroxyl OH, a byproduct of water molecules broken apart by sunlight, when the comet was still about 2.9 astronomical units, almost 3 times Earth's distance from the Sun. This is remarkable because at that distance, solar heating is weak and water ice sublimation is usually negligible. Yet the UV detection firmly indicates active water chemistry. From that signal, researchers estimated a water production loss rate of about 40 kilograms per second. They described it as unleashing water like a cosmic fire hose. This rate is among the most intense yet observed for any comet, especially so far from the Sun. What's more, the UV observation suggests that a substantial fraction of Atlas's surface is active. Models imply that at least 20% of its surface area is contributing to water outgassing. Atlas's early water activity reshapes how we think about comet volatiles beyond our system. In many known comets within the solar system, water becomes the dominant volatile only within approximately 2 to 3 astronomical units. To see water or its byproducts active at approximately 2.9 astronomical units suggests either unusual surface properties, extended sources of ice grains in the coma, or thermally efficient mechanisms heating subsurface ice. One scenario is that icy grains ejected from the nucleus drift outward and sublimate in sunlight, essentially acting as mini comets themselves, feeding the gas cloud around the comet. This would help explain how detectable water appears even where the nucleus alone might be too cold to sublimate itself. Another big twist comes from JWST, James Webb Space Telescope observations. Infrared spectroscopy of Atlas's coma revealed a CO2-dominated gas environment, with CO2 to H2O mixing ratios about 8:1, among the highest ever seen in any comet. In simpler terms, Atlas may have a nucleus intrinsically rich in carbon dioxide, or perhaps the sublimation of water is suppressed, meaning the gas output is dominated by CO2 even though water is present. Other observations from near-infrared and optical spectroscopy, Gemini IRTF, also detected water ice grains in the coma, and a red-sloped visible spectrum similar to D-type asteroids, suggesting dust with organic or carbonaceous compounds mixed with ice. Taken together, Atlas is not a standard comet. It's more chemically aggressive and volatile-rich than many comets we've observed. Based on the data so far, 3I Atlas behaves like an active, volatile-rich comet from another star system, not an engineered object. Its early water activity, dust cocoon, and gas emissions fit naturally within comet physics, albeit with surprising twists. The evidence strongly favours a natural origin. As Atlas nears perihelion on October 29, 2025, at approximately 1.36 astronomical units between Earth and Mars, it will become more active and easier to observe. We are watching a rare cosmic visitor in action, a messenger carrying chemical stories from another star system. Over the past decade, we've met 3 wanderers from the stars, 3 interstellar visitors, each profoundly different, each rewriting what we thought we knew about the space between the stars. One of the most compelling lessons so far is that every interstellar object has surprised us differently. Oumuamua was dry, odd, and accelerated. Borisov was a CO-rich comet, pristine and expected. Atlas is water-active early, CO2-heavy, and volatile in behaviour. The diversity challenges any single unified model of interstellar comets. It suggests that planet-forming systems across the galaxy may produce a wide variety of small body chemistries, volatile histories, and structural properties. If we've found 3 interstellar objects in less than a decade, how many more are out there? With upcoming surveys, especially the Vera C. Rubin Observatory and its Legacy Survey of Space and Time (LSST), astronomers expect we may detect dozens each year. Rubin's wide, deep sky coverage will catch even faint, fast-moving objects that would have slipped past older telescopes. Some will be dry and dark, some will blaze with gas and ice. And with luck, one day we might even reach one, sending a spacecraft to intercept a true visitor from another world.